Ashwa Kumar Kumar. Together with my colleague Muhammad Aizzat and Shaarwin, we are going to do finite element analysis on motorbike swing arm. Okay, our background study for this project is motorbike is known as one of the common transportation around the world. This is because it is very easy to maneuver around the city or small road. However, on the same road that the motorbike are using, there are a lot of bus and lorry going through it every single day. This will cause the road condition to get bad day by day. So, this will create a possible situation of swing arm break due to high amount of stress applied to it. To avoid this kind of situation, engineers carry out finite element analysis to know and improve the capability and performance of the swing arm. We have chosen a particular motorbike swing arm and we have drawn in SolidWorks and used it as a model. Okay, the problem statement is after we doing some research, we realized that the material used to manufacture the swing arm is aluminium. This is because it is lightweight and easier to mold into shape. So this particular part will be used as finite element model to understand more about the physical behavior and the most critical load case. Our objective will be carry out finite element analysis on the swing arm. The second objective will be analyze different types of load case applied to the particular part. In our case study, there are two possible load case which will be explained by my colleague Muhammad Aziz and Shaarwin. Okay, from that two load case, we will determine the most critical situation among the load cases that we will discuss in a short while.
Hello, my name is Muhammad Aizzat Ramle. I would like to present load case 1, the swing arm motorcycle hit by the speed bump. This is the material of swing arm, AI7075 T6SN. This is the properties that I get from the SolidWorks when I applied the material to swing arm. Next, the force applied at the swing arm. This is the dimension of swing arm. This is the weight of swing arm, and this is the weight of rider. So, we assume the time calculation, the time collision to the effect motorcycle speed, which is 0.3 seconds. This is the constant speed that we use to calculate 15 km per hour, and this is the degree of speed bump. With the information given, we calculate the impulse force, which is 426.74 Newton. Okay, this is for the weight of the rider and swing arm on the back wheel. This is the total weight, which is we times with 9.81 to convert in Newton. Next, this is the weight of back wheel that we get. We divide by 2. Next, this is the total force on back wheel, which is 764.21 Newton. Next, the weight distributed of the rider on the monoshock, middle axle, shaft and rear axle wheel. This is the calculation for the monoshock. This is the calculation for middle axle shaft, and this is the calculation for the weight rear axle wheel. This is the total force acting on the swing arm, 1439.14 Newton. This is the fix. In the mesh convergent research, we will mesh and run the finite element model with various element size to determine the ideal element size for obtaining the most accurate result. The finite element mode can only successful be meshed with element size 9.1 mm. Bigger than 9.1 mm, the mesh will be failed. Therefore, the element size range from 5.1 to 8.1 mm, which is 1.0 mm space between them. This is the size of element versus maximum von Mises stress. The graph 1 show. The graph 2 show the size of element in mm versus maximum displacement. This is the trend for the both of the graph. Next, This is the von Mises stress distributed plot. According to the stress distributed meter on the right side of von Mises plot, various color significant various amount of stress. Most of the region appears dark blue, which corresponding to the pressure of 935.5 megapascal. However, the back will support exhibit numerous color, indicating the region is under more stress. Next, the von Mises stress distributed. The right section, which is the close to the center axis, experience the most stress. The highest stress is indicated at the top of the stress distributed meter as 106.2 megapascal. As the result, the most cruel area of the swing arm, as illustrated in the diagram, is around the middle axis. The support position is the most important since the component that is farthest away from the main body. The front will took the burn of the force. We can also determine the material yield strength. This indicates the maximum stress has beyond the yield strength, indicating the swing arm will fail. The fix used in the simulation entries fix and hold the swing arm in place. Hence, this simulation is not accurate. Next, the displacement distribution plot. Varying color signify different displacement on the displacement plot, much as they did in the von Mises stress plot. Because it is fixed, the middle axis has a least amount of displacement. The maximum displacement is 1.819 mm, which is located at the hollow rectangle that support the swing arm construction at the rear. This is because the hollow rectangle holding the rear wheel framework took the burn of the stress caused by the rear wheel holding with the speed bump. Another reason is the hollow rectangle is a fixed last component, middle axis support. The displacement will be significantly smaller in real life since there are no fixes at the middle axis support. The swing arm rear wheel will bounce outward, creating less the displacement. Finally, the factor of safety distribution plot. This is the calculation to find the safety factor. The calculation safety factor is the same as the lowest factor of safety obtained in the simulation display in the top right of the factor of safety distribution plot. As the rear wheel hit the speed bump, this number of safety factor indicates that a section of swing arm frame will fail. In practice, the swing arm bouncing back will greatly lower maximum stress and hence rise the safety factor. The thickness of the rectangle of the swing arm should be increased to improve the design of swing arm. The material on other hand should be changed with one that has a highest yield strength. The swing arm will be able to take more stress because of this improvement. That's all from me. Thank you.
Hi sir, I'm Shaarwin Sivanathan. You would have heard from my colleagues Ashwa and Aizzat. Now I'll be continuing the presentation with the second load case, which is motorcycle cornering. Let me start with what and why motorcycle cornering. As we can see in the first picture, it describes the path during a motorcycle is cornering. So motorcycle is actually riding the motorcycle in a curved line during a turn. So why did we choose motorcycle cornering? Because it is one of the most common situations that every motorcycle will undergo frequently while riding their motorcycle. Okay. During motorcycle cornering, the rider have to lean their body in the direction of their turn to make a sharper turn, and so that they don't end up in their adjacent lane. So in order to stay in their lane, they have to lean their body during this cornering time so that they can get a sharper turn and stay on their lane. And during this cornering, the weight of the motorcycle and the motorcyclist will be applied on the swing arm as a force. So that force will cause stresses on swing arm, which we're going to analyze in the other slides. Okay, so this is the manual analysis that we did on the swing arm. So in this analysis, the two forces that will be applied on the swing arm is the motorcycle's weight and the motorcyclist's weight, which is 250 and 65 respectively. Okay, as we can see in the first picture, there is the weight distribution on the swing arm by the motorcycle and motorcyclist weight. So as we can see, the motor is actually leaning to the right. So as it is leaning to the right, the 70% of the total weight will be exerted on the right hand side of the swing arm, and the left hand side will only experience 30% of the weight. So in the second picture, we can see the total weight, which is the motorcyclist weight, 65 kilogram, and the motorcycle's weight, which is 250 kilogram, and we add up to get the total weight. And then in the third picture, we calculated the force that will be applied on the swing arm due to the weight, and then we divide it by 2 because the swing arm is only fixed at the back side of the motorcycle. So the forces will be acting on front and also the back, but we only analyzing at the back of the wheel where the swing arm is fixed. So we have to divide it by 2, and we only analyze at the back of the wheel. And then at the fourth picture, we calculate the force distribution on the swing arm, which is at the right hand side of the swing arm will be 70% and 30% at the left hand side of the swing arm. After that, at the fifth picture, we can see that we calculated the vertical component of the force at the swing arm. As we can see in the first picture, the force on the swing arm is actually at a I'm sorry for the mistake, it's actually 45 degree, not 40 degree. So the force is actually acted on the swing arm at a 40 degree to the y-axis. So it will give a two component on the swing arm. One is vertical component and also horizontal component. But for this case, we only analyzing the vertical component. So in the fifth picture, we can see we calculated the vertical component of the forces that acts on the swing arm. Okay, after this we move on to the final element analysis setup on SolidWorks, how we set it up in the SolidWorks. So as we can see, we have already did the SolidWorks for the SolidWorks design for the swing arm. This is our design, and there will be two forces added on the swing arm. One is on the left, which is the orange color, and one is on the right, which is the purple color. The orange color will be the 30% of the total weight that we calculated in the previous slide, the vertical component of the 30% total weight, which is 327 and 76 Newton. And the purple color on the right hand side of the swing arm will experience the 70% of the vertical component of the total weight, which is 764 and 77 Newton. We move on to the stress distribution on the swing arm, which obtained from the SolidWorks analysis. This is based on the von Mises stress criterion. So based on this first figure, we can see the stress is distributed along the swing arm, and the color of the swing arm shows the stress distributed on the swing arm, where the warm region has a high stress and the cooler region, which is the blue color, shows lesser stress, and where the smallest stress in the swing arm is 51.49 Pascal, where the most critical part in the swing arm is actually at the joint of the front axle, where you can see it in the second picture. So at that joint, we can see a red color spot at the top and the bottom part, where it is the most critical place where the highest stress is actually experienced by the swing arm. The highest stress in this swing arm is 53.08 megapascal, and for this material that we choose, its yield strength is 505 megapascal, which is way high than the highest stress experienced by the swing arm during cornering. So it well suggests that the swing arm will not fail during cornering. Alright, this is the analysis on the swing arm's displacement. Okay, as the previous analysis, this is same as well, where in the first picture we can see the displacement distribution along the swing arm, and the cooler region shows lesser displacement, and the warmer region, the red color, shows high displacement. As we fix the swing arm at the front axle, we can see at the front axle it is covered with the blue colored region, which gives us a displacement of a very significantly low value of 1 times 10 to the power of negative 30 meter, which is very significantly low, since it is fixed at that end. And then the most critical part in the swing arm is the rear axle at the back of the swing arm. As you can see in the second picture, it is colored in red, where the highest displacement at that place is 0.825 millimeter. But this displacement will be even smaller in real life situation, because during cornering, the tire of the wheel of the swing arm, the wheel of the motorcycle tends to move upward, will also make the swing arm to displace upward, which will make the displacement at the end part to be even more smaller. Okay, finally the analysis on the swing arm will be its safety factor. Okay, we gotten the highest stress that will be experienced by the swing arm during cornering on the previous slides, which is on the analysis of stress. We gotten the highest stress, which is 53.08. Using that stress, we can calculate the safety factor of the swing arm manually, which we did in the first picture, which yields a safety factor of 9.51. Okay. After that, by observing from the safety factor that we obtained from the simulation, we can see the 9.51 safety factor is the lowest, and the maximum safety factor that can be achieved in the swing arm is 9.8 times 10 to the power of 6. Okay, and also, so from this, it tells us that during cornering, the swing arm requires at least a safety factor of 9.51 to sustain the load without failing. And if the safety factor goes below 9.51, the swing arm has a high possibility to fail. So that is all from me. Thank you.
After a few discussions among ourselves, we came to the conclusion that the most critical load case for the swing arm is load case 1. However, the result from the analysis is not accurate, as there will be no fixture to the swing arm in real life situation. This means that the maximum stress applied to the swing arm will be reduced significantly. However, there will be few changes need to be made in order to make the swing arm more reliable. Not to forget, the objective for our case study has been achieved as well. Lastly, we would like to thank Dr. William for giving us this opportunity to carry out this case study, as we learned a lot of things and how to do analysis in SolidWorks in a correct way. Thank you.